Cool. Hey, everybody. My name is Chris Mortonson, and I am one of the developers on Pokémon GO. So it's been a kind of a crazy year for us, and I wanted to share with you one of the aspects of building this game that went really well. I've been using Unity for a long time, and throughout that time, generally each game has gotten progressively a little bit less of a mess. But this is really the first time that I felt like we didn't have a totally unwieldy code base by the time we launched the game. This talk is going to be about how we approach Unity to make a long-term sustainable game without sacrificing any of that core Unity goodness. So for, I don't know, maybe one of you doesn't know what Pokémon GO is yet, so I'm going to give you a quick context. This is our launch trailer. OK, so there's a lot of stuff in our genre that is not quite traditional. Pretty much all games require a ton of iteration to become fun, but many aspects of game development are kind of solved in some ways. For example, we kind of agree on how console first-person shooters should control or really like the behavior of a 2D platformer. I'm not saying these are easy to implement well, but most games get to have a lot of benefit from the existing game mechanic zeitgeist. Pokémon GO didn't really get to leverage very many of these traditional decisions, so we knew from day one that we were going to have a very flexible infrastructure. We're going to need to be able to iterate all over our code base in weird places for lots of reasons that we can't predict. Well, Unity naturally gets the user into really good habits for prototyping and iteration. It doesn't really do much for you for getting into a long-term maintainability process. So I've been responsible for a whole bunch of smelly code bases in the past. It's kind of natural when you're shipping a game. You're crunching right near the end. The key is really to find the correct balance of pragmatic engineering that lets us focus on the game without creating a mess. And it's really difficult to plan this out ahead of time. Over time, your systems grow and become more difficult to adapt. And as developers, we really need to strive to preserve that spirit of prototyping and iteration as the project grows, or we're really wasting kind of the best part of Unity. So just some background context. A traditional non-Unity project gets set up like this. You create an entry point, and you have a cascade of systems, and those systems might interact and pass through things to each other. You might create a bunch of singletons to facilitate communication between the systems. It works. Maybe there's room for improvement here, but it's fine. It doesn't work in Unity, though. Every mono behavior has its own entry points, and there's a lot of them. Or you can try to reinvent the wheel and not use a lot of them. I don't recommend that. Anyone that's attempted to use the traditional singleton pattern in the Unity editor pretty quickly learns that the magic of C# context living through play sessions is going to mess that up. And of course, Unity's serialization system means that you don't get constructors. A lot of that might sound like a criticism of Unity, but it's not. Those are design choices that they made in order to enable us to prototype and iterate faster. OK, so this is getting into our approach. And I've heard actually dependency injection mentioned a whole bunch of times throughout the last couple days in talks. And I'm going to kind of go into exactly how our approach to that worked in Pokemon Go. So on the left here is normal polymorphism. You can see on the map there's a whole bunch of different Pokemon that have spawned from different sources. There's incense and lure modules and wild spawns. And when the user interacts with one of those, they go into the encounter scene there. The encounter scene doesn't care which type of Pokemon you got. This is normal polymorphism, and it's a good thing. A lot of people are probably doing this all the time. The example on the right has that same kind of polymorphism, but flipped. This is a concept called inversion of control. Each object is responsible for asking what systems it wants. This is a really good fit for Unity because you don't have constructors and monobehaviors. Your monobehaviors can go out and just get the things they need. Ends up getting into a much better pattern. And also, this is like the core concept that dependency injection is built on. You don't really know exactly what you're getting, but you just need something that kind of works for this system. This really enables a whole bunch of cool patterns. So this is what a traditional dependency injection setup looks like. With dependency injection, during setup, each system is created and then installed in the composition root. You can think of the composition root as a fancy dictionary that keeps track of all your systems by their interface types. When I write code that needs a reference for, say, the input manager, my class just asks for it, and the dependency root just gives me whatever I installed for that. We built our implementation off a library called Zenject. It's free and on the Unity Asset Store. There's a few other libraries available for Unity, and for the most part, they're going to provide the same basic features. So just really, if you want to try this out, do whatever one looks good to you. I'm not going to go into any of the specifics on those frameworks here. I just want to illustrate at a high level what you can do if you take this sort of approach. So last slide was set up. This is when you actually want to use the thing. In this case, I have my very simplified map gym here. When it's created, it's going to ask for a handful of systems. In this case, the camera rig, the input manager, music service, and the world map state. Whatever was installed to the composition root gets tossed into your mono behavior here. And you can see it interacts with traditional serialized fields in Unity just fine. OK, so that's the basics. And here's what it actually allows you to do. For starters, the setup allows your system to play much nicer with Unity. You don't have singletons all over the place. They're all kind of managed by your composition root. It's a lot easier to prevent yourself from making mistakes about things like not clearing properly. And without doing this sort of thing, you end up having to futz with the script order of the order of execution. And anyone who's actually done much with that knows it's pretty error-prone. So here is a pattern that we did a lot. This is for tools. What happens is I have the same map gem here, and it's just injecting much simpler services. This is a tool that we basically sliced out the gym itself so that our animators could mess around with how it behaves on the map. The composition root just has mock classes installed for many of the systems. For instance, the simple version of the map renderer we're using here is just a quad, and it tells the gym to position itself at the origin, regardless of what the gym thinks its lat long is. And because it's easy to set up and maintain these mock composition roots, we really have a reliable way to slice out systems from our main code in order to rapidly iterate on them. Over the course of making Pokemon Go, we probably ended up making a dozen or so of these tools that let us focus in and iterate on critical portions of the gameplay. When you make a scene like this, it feels very much like you have that Unity magic where prototyping is easy. But because of the abstraction of dependency injection, the work that you do here is automatically applied back to the rest of your project. Another case that would be kind of similar to this that we didn't do in Pokemon Go is, say you had like a MOBA, for instance. You might want to really iterate on your core character controls and all that stuff, and then you're going to put that into different gameplay modes. This is also a spot where dependency injection is going to shine. You can have your game mode as the whole outside services that get added in, and you have your core thing that you can iterate and move around between scenes. It works great. Because it's easy to create these kind of mock composition roots as scaffoldings around your code, means it's really easy to unit test all your code as well. And when tests are easy to make, they actually get made. It's kind of important. And if you want to iterate quickly on your code, I really recommend trying to test as much as possible. And to a lot of people, that seems counterintuitive. But really, what happens is the more well-tested your code is, say I need to change system B over here, and system A is well-tested, all the changes I make to system B here, I'm reliably not breaking system A. It really is having tests all over the place is what enables you to really iterate on things quickly. Otherwise, you're going to break stuff, you're not going to know it, and you're not going to find out until you have a QA iteration, and that's going to sap your productivity later on. Another side thing here, if anyone's used nsubstitute before, this sort of setup works perfectly with it. Everything is an interface that gets injected here. So you can see I have the camera rig and the input manager and the music service being set up for this test. I'm just calling substitute for on those things. I don't actually have to make a mock class for those things. It's just straightforward. I can just toss a thing in there, test run. It's great. So here's what the actual test looks like for our map gem here. Container.resolve on the first line there is actually pulling out a map coordinate service that we created and mocked out. And then it's just configuring it that when something asks for a default lat long, it's going to return a specific value. We build it, and the verify is just making sure that it gets that value there. Really simple test. This is just the pattern that goes all over the place. So all this stuff is really cool, trying to make my case for using dependency injection, but there's still one problem with Unity, and that is this composition root where you end up kind of creating a stock drawer of all your systems. If you're using prefabs to store a lot of these things, like prefab serialization, which is what we did, you're going to end up with one gigantic prefab, which will just be a nightmare anytime anyone edits it, because you're going to have merge conflicts and all sorts of problems. What we like to do is split everything up as small as possible, and really, we don't want to store anything in a scene file for all these reasons. It just makes it a lot easier to work together. Because we wanted to not do this, we had to come up with a different solution for installing all of our systems. And to do that, we decided to leverage our game states. So most games have game states of some form. We use ours to transition between different levels and game modes. Ours are laid out on disk as small prefabs that just reference each other. And this is the backbone of how we manage everything in the game. If something's not linked in at some point to a prefab, when we hit build, it's not going in that build. So the main scene is basically just like one root game object, and it spiders down to the rest of the scene. And so in this scene here, we're starting up the game. We only have two active states, the root state and its child boot state. So once we've transitioned out of boot state, for the sake of this example, we're going to be in the new user sequence. You can see that we have 4 active states now, and boot state's been disabled since it's been completed. A good rule of thumb is when you create your states is that at any point, if you were to print out what the active states are, you'll have a really good idea of what the player is doing at that time. In this case, you can see the users on the world map for the first time looking at the starter Pokémon choices. So once the player has chosen their starter Pokémon, transitions into trying to capture them. In the actual game, there's probably a dozen or so states here. This is just kind of an example. For simplicity, I'm just showing you the main ones here. In general, the more fine-grained your states are within reason, the better you'll be able to iterate on them. The encounter state here has actually injected all the references for the throwable Pokeball, the 3D scene, the UI. There's no need for the parent states to pass anything down. It just really simplifies all of your dependencies. So this is kind of how we keep those states small. The root state there is just a few serialized references. The YAML file for that prefab is tiny. It's easy to maintain. And it references each of its substates, and those substates reference further down things, creates a tree that spiders your whole code and really becomes the backbone of all of your code. This is also the skeleton that we used for our dependency injection. Instead of having all of our systems installed in one place, we let each state install whatever systems that they're going to need. To avoid all the boilerplate code that would be involved with having a ton of those distributed installers, we actually used C# attributes to signify what prefabs should be installed and how they're used. If any of you saw the editor VR talk earlier, they did something very similar. Instead of attributes, they were using interfaces. So if you implemented iTool, they had a thing that would automatically take that and inject it and be able to use it as a tool inside of the editor VR. It's really cool. This is basically the same thing with a little different syntax. So this is what that looks like. This is just a normal, or the top part here is just a normal Unity serialized reference. In this case, it's our world map state. It's going to maintain everything for when you're walking around on the map. And the attribute up top is basically just saying how it gets installed. So when something else, some other piece of code asks for a world map state, which is the bottom example there, it's going to have a copy of this prefab instantiated, and it's just going to get a reference to it in the actual game. If this were in a tool or in a test, it still just asks for the world map state, but it might get a completely mocked out object. One of the cool things about this is it really has very little cognitive dissonance while you're coding. The dependency injection attributes here for both install prefab and inject, they feel a lot like using Unity serialization normally. They're just kind of like, I'm setting up my mono behavior, and I want to get these things into it. And you can just mix and match it with the normal serialized references that you want for all your knobs for your designers and artists. So by taking this recursive approach through our states, we can now scale our game without having to scale our composition root game prefab. On the right here, this is the code basically for what that composition root looks like. It has a reference to the root state, and then we call recursively bind, and it's just going to traverse the whole thing, find all those attributes, install them as you requested. And then this file never changes again. As we add new systems later on, we don't touch this. It's done. So this is when the first level, as it's recursing, it gets a copy of the root state here. It has references to its child states. At runtime, our state can use these systems as usual when the different state transitions happen. In this case, our root state immediately selects its boot state. When boot is complete, it'll either go to the first-time user state or the world map state, depending on if you're a first-time user. Some of the caveats to worry about here, because it's recursive, you got to make sure that you're not doing something like installing on a character that has a very complicated set of bone hierarchy or something. You don't want to waste time traversing something that's going to have nothing in it. So what you do is you make sure it just looks at mono behaviors and just make sure you're not referencing something like a character straight up. And there's different attributes you can create to manage that sort of thing. So this approach just really lets us scale our project out while retaining all the Unity magic that lets us focus on prototyping and iteration. We can keep using this. We can scale out our systems throughout the game wherever we want. And each system gets to be well tested, so we don't have to break it all the time. This is really important for us at Niantic. We build games for the long haul. If anyone's familiar with our first game, Ingress, that's still going strong after 4 years. We're going to need to be maintaining Pokémon GO for years to come. The systems I described here are all coming together to make one of the best code bases I've worked in and are part of our strategy for bringing players adventures on foot for a long time to come. So if this sort of thing is interesting to you, we are hiring. Before we get to the Q&A here, I just wanted to put out a disclaimer that I'm not really the right person to answer any product questions, but I'm happy to answer any sort of technical C# Unity stuff. So thank you. The question just now was which DI library are we using, and we're using Zenject. I also looked at Strange IOC. They're both pretty cool.
Hi, question for you. Is your scene loading in this game single scene or multi-scene?
We have multiple scenes, but they don't really do much, just basically for some async loading stuff for optimizations. For the most part, you could just consider it one scene. And we use our composition root and game states basically instead of scenes, although it's totally, depending on a different sort of game, you might absolutely want to have your states load different scenes. The way that our infrastructure is set up, we create this whole network of states, and that whole thing is set up as don't destroy, unload, so we can move around between scenes if we want to.
Okay, so you guys don't necessarily like stack Unity scenes on top of each other. It's just single scene mode.
Nope. Although we could totally do that if we needed to. We just decided not to. Like the nature of streaming in map data doesn't really get us much for having scene files. We don't get to serialize a whole lot. Everything's kind of dynamic.
Cool. Thank you.
Yep.
So one of the things that I've seen, problem I've seen with dependency injection is in the composition root aspect. Sometimes some of those objects require other such objects. In the preloaded composition root type thing, you end up having to order things very appropriately to get them done in the right order.
Yep.
In your method of doing things with attributes and basically just in traversing your tree, how do you handle that ordering?
Cool. So yeah, and just a little bit of context on this before I get into it as well. This ordering, like where things need to reference each other, is actually a really good thing about dependency injection, and it's the reason why I think dependency injection works better than raw singletons. Because with your raw singletons, if they need to reference each other, you don't have as much control over the ordering. In our case, the way that it works is two phases, and so a lot of things will actually be created before they're injected. So it can handle circular dependencies, although I make it throw a warning just to say, like, you're probably not designing this well if you need to do that. So we don't actually have any warnings being thrown when we do that. It's just there for as you're developing, like, I don't want to get in your way for whatever you're working on, but you probably don't want to check this in. So when you have that two-phase startup like that, you don't really run into the issues as much. Like I know what you're talking about. Like I've used it before in like AngularJS has a huge dependency injection thing, and you have to like do some sort of awkward after the fact. But really, at least for the way that we have it set up in Zenject, everything's kind of that after the fact. So it just kind of cleans up the problem. I think it's kind of a solved problem in a lot of ways.
Yeah, the problem can happen when you've got not necessarily a circular reference, but when you have something, if one thing needs object type A, and object type A hasn't been seen in your tree yet, then it gets back a null at that point because it doesn't have that thing available.
Yeah, so the way, and I can only speak to Zenject here, it does a good job of ordering those things for you. That's with the two-pass, it can see what, everything's getting created, what is it going to need, and then it orders things properly based on that. So yeah, in a lot of ways, it's automatic.
With some of the unit test code that you had written, I noticed you were instantiating game objects. Can you talk a little bit about how you've gotten around the awake update, like those type of callbacks, and any advice you have on unit testing in that way? Yeah,
so we have a couple things that we added. We have a monobehavior test helper class that just has a few basic reflection functions in it. I say basic, it actually is really easy. I know reflection sounds kind of scary sometimes, but it's not. In this case, what we do is there's one helper class we add to monobehavior when you're in our test namespace where you can just get invoke Unity function, and we try to replicate the same way that Unity finds your function calls. We just find the same thing. So a lot of times we have tests where we've mocked out like time, and say something has to happen after a second, so it'll happen in the update loop. We can move time forward to like 1.1 seconds, tick update, and then check that thing happened. It's actually not too hard for all the things built into, for all the things that are like by default in monobehaviors. The one area that we had a lot of trouble with was you can't really test anything that touches a coroutine. So in our case, we just rewrote coroutines. I've seen that across a lot of projects.
Hello. How much of the performance issue the dependency injection was for you? Did you cut since it's reflections based, probably, so did you have to cut it out in some performance critical parts of the game? Because we, for instance, use strange IOC a lot in our game, and we ended up cutting out from the gameplay because, well, it's just too much happening at the same time, and the reflections basically screw it up.
So yeah, I'm not sure what Strange IOC does for this. Zenject does a really good job of caching, so you incur the reflection cost only the first time you create a thing. So for all of the core systems that we build during startup, that's not so much of an issue. That's hidden behind the loading bar. But when you're doing things dynamically, like emitting, in the case like you're moving around the map and you're emitting Pokestops and gyms, those things get injected. You only incur that performance penalty on the first time, and then it remembers how to deserialize your object for you from then on.
Okay, so basically you kept it for everything, you didn't cut it.
Yeah, I mean, it's pretty similar to just instantiating normally once you eat that first instantiation cost. And it hasn't really been enough, like on Pokemon GO, we didn't really notice, that never became a bottleneck we had to optimize.
Okay, yeah. Thank you.
Hey, don't know if it's relevant, but I was a bit curious about the architecture outside Unity, like game servers, languages, databases, protocols, networking.
Yeah, so our platform, I'm a client engineer, so I can't speak to a lot of that. But there's actually some cool article you can read about that came out recently from the Google server engineering team. We use Google as our backend. They talk a lot about what they had to do to support our kind of crazy number of users. So I recommend looking up that article, and you can read some good stuff about it there. Thanks for coming, and if you want to ask any more questions about Pokemon Go, I'll be around for a bit.